Okay, let me give a brief introduction to this chapter on cryptography. I'm sure you've seen secret messages on cereal boxes and whatnot. So the purpose of this talk is just to introduce some terminology. I'm pretty much going to follow the chapter. When you want to send a message, the message you want to send is called a plaintext. The encrypted message, the message that's encoded, is called a ciphertext. The plaintext and ciphertext are both written in an alphabet, where each item in the alphabet is either considered a letter or a character. You could use numbers, you can use letters, and so on. A crypto system is a complete system for sending secret messages. It includes both encryption, which means making the secret message, and decryption, which means recovering the original message that was sent. Usually these crypto systems are based on a function called a key. An encryption function is called a key. Usually encryption involves both a method and a number or symbol or string of letters known only to the person who's using the system. So that secret thing is called a key. Just like a key can open a lock, you have to have that particular key. So in order to be able to encrypt, you need to know that particular string of letters to do the proper encryption. So follow this example down here. Suppose person A wants to send secret messages to two different people, and he doesn't want them to understand each other's message. Now he can use the same method to encrypt, but he has to use two separate keys so that B can't understand C's message and vice versa. All right, this page talks about the difference between public key and private key crypto system. Public key means that the encrypting key is known to everybody, but only the person who receives it knows the decrypting key. Okay, so public means that everybody can know it, but it's still secret, and only one person who knows the secret decrypting key can decode the messages. In private key crypto systems, the person who's sending the message and the person who's receiving the message must both know the key. So that's the only way it can work. So here's one example. You've probably seen this again on cereal boxes. You take all the letters and you shift each letter by 3, and then you get, for instance, you get this message, Dodge Hood. And if you know that Dodge Hood is created by shifting each letter by 3, you can just shift each letter back by 3 and get algebra. So that's a very primitive crypto system. So this page discusses different ways to decode messages. Often you use statistical analysis. For instance, if it's a letter-by-letter encryption, you look for the most common letter. You've probably done cryptograms in a newspaper or something like that. You use this kind of method to decrypt. Okay, these are examples of monoalphabetic crypto systems. It's basically one for one. There's one letter in the encrypted message for each letter that is sent. But there are more sophisticated crypto systems, as we'll see. All right, he gives another example of a monoalphabetic crypto system. Here, rather than just shifting the letter by a certain amount, first you multiply and then shift by a certain amount. So this is a little bit more sophisticated, a little bit harder to crack. Now you have to be able to decode. In order to be able to decode, this function must have an inverse. So that's what he has down here. That's the way it goes. If you want to recover the encoded message, you want to recover the decoded message from an encoded message, you have to be able to undo the function. So the function that encodes must have an inverse. Now, one way to make the encoding function a little bit more secure and sophisticated is to use a polyalphabetic crypto system. You don't encode one letter at a time, you encode multiple letters at a time. Now later on we'll see when we're talking about communications codes, this same method is used not to make the message secret, but to make it so that noise in the system or errors in the system can be identified and the original message can be recovered anyway. So we'll see that in the next chapter. So suppose we want to encode a pair of letters at the same time. So this P denotes a pair of letters. So you can think of these letters. Of course, we'll turn the letters into numbers. And we can think of these numbers as entries in Z26. Okay, because there are 26 letters, so we're going to represent each letter as a number from 0 to 25 in order to get Z26. Okay. We can define this matrix operation. Now here this matrix multiplication is matrix multiplication in Z26 because we want to get a result in Z26. Okay, so if we do this encoding operation, we're going to have a decoding operation, and we use matrix algebra, which still holds even if we're doing multiplication in Z26. We can derive this inverse function, and that's the way to recover our original message. So let's look at this example. Suppose we want to encode help. There's 4 numbers corresponding to the usual correspondence. And then we create this matrix here. Then we have this inverse matrix here. We find inverse matrix by the usual inversion methods. And if you follow through and do the arithmetic, you'll find that the message comes up with a set of 4 numbers, and those 4 numbers turn out to correspond to RRCR. Okay. This works very well, much better because because the encryption depends on pairs of letters, and pairs of letters are not so easy to identify. For instance, E is often a letter in English, but there's not too many pairs of letters that appear very often. TH is one, but it's harder to identify these pairs. Okay, finally, there's this topic, public key cryptography. In this, of course, public key means that everybody knows the key. Everybody can encode the message, but only one person can decode the message. What that means is the person who can decode the message has special knowledge about the structure of the key. Only the person who decodes the message knows what F inverse is. F is open, but F inverse is difficult to compute. This seems quite strange, but it's in fact possible, as we'll see. All right, the last topic in the chapter is this RSA cryptosystem, which is widely used in computers and in communication. And here he goes through a description of how RSA works. And in class, I'll ask you to try to duplicate this description and do the encoding and decoding. It's a good exercise. The whole algorithm depends on number theory. And I think the best way to understand RSA is to work through example. He does an example here. And like I said, I'll have you do some examples in class. Now in this part, where he talks about message verification, he talks about an intriguing problem. He says that anybody can send an encrypted message. So how do you know the encrypted message is from the person that you want to receive the encrypted message from? Now in this situation, the 2 people who are communicating both have their own encryption and decryption keys. Bob's is E prime for encrypting, D prime for decrypting. Alice's is E for encrypting, D for decrypting. Okay, and Alice wants to know that Bob actually sent the message. So what Bob does is he decrypts with his own key and then encrypts with Alice's key. And then Alice does it backwards, and Alice recovers the original message, and she realizes that since only Bob could decrypt the message that she uses his key to encrypt, it must have been Bob who sent the message. All right, in that short description, it's a little bit tough to follow, but read the description and you can understand how this works.